Hey dear data enthusiasts, and welcome back to my channel.
Today, we're diving into the details of dimensionality reduction, one of the most important data preparation techniques for machine learning. We will be focusing on two techniques, feature extraction and feature selection. Most importantly, we will be learning how to implement both these techniques using Python and R. So let's get started. Before we start coding, let's recapitulate the definition of dimensionality reduction. Dimensionality reduction is a technique used to reduce the number of input of variables in your dataset. Using dimensionality reduction, we'll make sure that our machine learning models perform faster, more efficient, and potentially more accurate. Remember, there are two main techniques of dimensionality reduction. Feature selection, selecting the most important features. Feature extraction, creating new features from the existing ones. In this video, we will use Principal Component Analysis, PCA, for feature extraction, Recursive Feature Elimination, RFE, for feature selection. We start with PCA demonstration using Python. In this tutorial, we will be using the breast cancer dataset from scikit-learn library. The breast cancer dataset, also called the Wisconsin Breast Cancer Dataset, it's a commonly used dataset in machine learning used for binary classification tasks. This dataset is ideal for evaluating the performance of machine learning models and techniques like dimensionality reduction, as it contains multiple features. So before we run PCA, let's find out more about this dataset. This dataset contains 569 rows and 30 features, plus one target variable. The target variable represents the type of tumor. 0 means malignant, cancerous, or 1, benign, non-cancerous. The 30 other features represent various characteristics of cell nuclei, derived from digitalized images of breast tissue. These features are computed based on the shape, size, and texture of the cells. So given that this dataset contains 30 features, makes it a good candidate for principal component analysis, because it helps reducing the dimensionality while retaining the most of the variance in the dataset. PCA can reduce redundancy by transforming the features into a smaller number of principal components that captures the most important variance, simplifying the model and making it faster. So let's get to the coding fun. First, we need to import the necessary libraries. We import pandas, use it for data manipulation and analysis. Next, we use it scikit-learn.dataset model to import load breast cancer function to load the breast cancer dataset, which we will use in this tutorial. Then we import the standard scaler. We will use it to standardize features by removing the mean and scaling the data to unit variance. Standardization is a common requirement before applying PCA. If you want to know more details about standardization and how it works, you can watch the first part of data preparation for machine learning. Finally, we will import the class PCA, use it for performing principal component analysis from scikit-learn.decomposition model. We will use PCA function to reduce the dimensionality of the data, to transform the features into smaller set of new features called principal components, while retaining the most of the feature variance. Next, we will load the dataset using load breast cancer function. This dataset is stored as a dictionary-like object, which contains both the features and the target labels. Now, we need to extract the features matrix X from the dataset, which contains 30 features for each of the 569 samples in the dataset. This is a 2D array where each row represents a sample and each column represents a feature, like mean radius, mean texture, etc. Then we extract the target label, which classify data or tumors as malignant 0 or benign 1. Let's run this code. Now we need to normalize the data before applying PCA. This step is important because PCA is affected by the scale of features. To do this, we first define our scalar, using an instance of standard scalar class. Then we standardize the feature matrix X using the fit transform. Fit calculates the mean of standard deviation for each feature. Transform standardizes the data, subtract the mean and divide by the standard deviation. So all features will have the mean of 0 and the standard deviation of 1. To apply PCA to reduce dimensionality of the dataset, we create an instance for the PCA class. We specify that we want to reduce the data to 5 principal components using the argument n components equal 5. This way, we tell PCA that we want the top 5 components that explain the most variance in the data. This line here applies PCA to the standardized dataset using the fit transform method. Basically, fit learns the directions principal components that maximize the variance. Transform will then project the original data into 5 principal components, effectively reducing the dimensionality of the data from 30 features to 5 principal components. The result XPCA is a new dataset with 5 features that represent the transformed data along the principal components. Now, we will create a pandas data frame using the PCA transformed data. The columns argument assigns meaningful names to the columns, such as PC1, PC2, PC3, till PC5. PC1 stands for Principal Component 1, and so on so. Then we add the new column target to the data frame. This column will contain the original target labels, malignant or benign, so that we can associate each reduced observation with its class. Finally, we can display the top 5 rows of the data frame using print function. This is useful to check the transformed data after applying PCA, showing how the original 30 features have been reduced to just 5 principal components, along with the corresponding target labels. In this example, we reduced the dataset from 30 dimensions to 5 using PCA. This allows us to retain the majority of the data's variance while working with a much simpler dataset. With 5 components, we can still capture 84% of the variance in the original data. Now, let's see how we can apply PCA to the breast cancer dataset in R. Similarly to what we did in Python, we will reduce the dimensionality of our features from 30 to 5 dimensions. First of all, we need to load the necessary libraries. In this tutorial, we will need Caret, a library which is commonly used for creating predictive models, processing data, and handling machine learning tasks in R. This library will help us with scaling and other data processing steps. Next, we need to load the breast cancer dataset from the MLBench package. If the MLBench package is not on your computer, you can install it using install packages, MLBench, and there you have it. Going back to our dataset, this dataset contains information about breast cancer tumors, which is usually used for classification tasks. We then remove the ID column. The ID is not useful for PCA or machine learning since it does not contain information relevant to the classification task. The dataset might contain factor variables, which means categorical data stored as level. We use lapply to apply a transformation to each column of PC data. Then we convert factor levels stored as characters into a numeric value. This line ensures that all factors are converted into numeric data, which is necessary for PCA, as PCA can only handle numerical data. To ensure that all features are on the same scale, which is important for PCA, we need to standardize the features into the dataset by subtracting the mean and dividing by the standard deviation. This line excludes the target column class, which contains the labels malignant or benign. We don't have to standardize or include the target column in the normalization process, as it is not used by PCA, seeing that it's not part of the features. The scale function will center the data, mean of 0, and set a unit variance, standard deviation of 1. To apply PCA, we use the function prcomp to the standardized data. We use center equal true to center the data, subtract the mean from each feature, scale equals true to scale the data so that each feature has a unit variance. The error over here is due to the existence of NAs in our data. To overcome it, we just need to omit any existing NA in our data. We do this by NA dot, and then we apply our PCA. The result of this function is a PCA model object that contains the transformed data, principal components, and information about how much variance for each component explains. We extract the first 5 components from the PCA result. Each column PC1, PC2, etc. represents a new feature created by PCA, which is a linear combination of the original features. Then, we create a data frame that include the first 5 principal components and the original target labels, the class column, so you can still identify which samples are malignant or benign. After dimensionality reduction, let's display the first 6 rows of the transformed dataset. This is a useful way to inspect how the dataset has been reduced and transformed into principal components. We can use ggplot2 library to create a scatter plot of the first 2 principal PC1 and PC2 with the points colored by target label, malignant or benign. JOnPoint adds the points to the plot representing each sample. ggtitle adds the title to the plot. This visualizes how well PCA separates the 2 classes, malignant versus benign, in a lower dimensional space. So, we used R to run PCA using the function prcomp, and we visualize the first 2 components with a scatter plot. This gives us a clear picture of how the species are distributed along the new dimensions. Alright, let's move on to feature selection using RFE in Python. We'll use Recursive Feature Elimination to select the most important features in breast cancer dataset. Before we dive into the code, let's break down the algorithm's key process of Recursive Feature Elimination. Recursive Feature Elimination, or RFE, is a powerful technique used to select the most important features for your machine learning model by eliminating the least important features recursively. RFE works by first training a machine learning algorithm, such as a decision tree or logistic regression, on the entire set of features to assess the importance of each feature. The model evaluates each feature's importance and creates a ranking. The feature with the least contribution to the target variable is identified. Once the least important feature is found, it's eliminated from the dataset. RFE repeats this process, training the model on the repeated dataset, ranking the features and eliminating the least important feature one at a time. The process continues until a predefined number of features remain or another stopping criterion is met, leaving us with the most important features that will improve the model performance. Using recursive feature elimination allows us to focus on the most critical features, reducing noise and improving the model's efficiency without sacrificing accuracy. Now that we know what's going on behind the scenes, let's find out how we can apply it using Python. First, we need to import the necessary libraries. RFE is imported from sklearn.featureSelection. Remember, this is a technique that recursively removes features and builds the model on those that remain, to rank and select the most important ones. Logistic regression is imported from sklearn.linearModel. It's a machine learning model we will use in this example to evaluate feature importance. Second, we need to initialize the logistic regression model. We will use the argument maxIter equals 1000 to ensure that the model has enough iteration to converge, since logistic regression is an iterative algorithm. If it doesn't converge, the model stops after 1000 iterations. The logistic regression model will be the base model for the RFE process, which will repeatedly fit the model to different subsets of the data to evaluate feature importance. Next, we will apply RFE. RFE is applied here, and it uses, as explained, the model parameter, which is the logistic regression model, to evaluate the importance of each feature. And the stopping criterion and features to select will be set to 5 to indicate that we want RFE algorithm to stop measuring the importance of features when we reach the top 5 features. So RFE will eliminate features one by one until it finds the top best 5 ones. The fit method applies the RFE algorithm on the features matrix X and the target variable Y. X is the feature matrix, in this case, the data from the breast cancer dataset. Y is the target variable, the class label for cancer diagnosis in the dataset. In this step, RFE will train the logistic regression model on the full set of features, rank the features by importance, remove the least important feature, and retrain the model. Continue this process recursively until only the top 5 features remain. Finally, we can check the selected features as follows. After applying RFE, we use support and ranking attributes to understand which features were selected and their ranking. Fit.support, this returns a Boolean mask, an array of true and false, where true means the corresponding feature was selected as one of the top 5 features, and false means it was not selected. This basically shows which features were selected. Fit.ranking, this returns an array where each feature is assigned a rank. The rank of 1 means the feature was selected, and higher number represents the order in which features were eliminated, which means less important features receive higher numbers. This tells us the ranking of the features, where 1 indicates the most important features selected by RFE. To sum up, in this tutorial, we imported RFE and logistic regression to perform feature elimination. We initialized the logistic regression model to evaluate feature importance. We applied RFE specifying that we want to keep 5 features only. We trained RFE on the dataset and it recursively removed features, leaving us with the most important ones. Finally, we printed out the selected features and their rankings, showing which features were chosen by RFE as the most important for the model. This is another simple yet effective way to simplify high-dimensional datasets. Now, let's implement RFE in R. We will use caret package to perform feature selection and pick the most important features from the breast cancer dataset. Similarly to what we did using Python, we will use RFE to select top 5 features by evaluating their performance to reduce the dimensionality of the breast cancer dataset without losing key information. So, we start by loading the necessary library. Remember, caret is the most commonly used library in R for building and evaluating machine learning models. It also includes utilities for feature selection like recursive feature selection, which we are using here. Now, we need to define the control using RFE. RFE control is a function that sets up the control parameters for RFE algorithm. It defines how the RFE process will be carried out. Functions equal RFfuncs. This algorithm specifies the function to use during RFE. In this case, we are using RFfuncs, which is a predefined set of functions in the caret package designed for random forest feature selection. The method CV is defined the method used for resampling. Here, CV stands for cross-validation. Cross-validation is a method that splits the data into subsets to train and test the model multiple times, ensuring the results are more reliable. Numbers equal 10. This set the number of folds for cross-validation. In this case, it is a 10-fold cross-validation, meaning the data will be split into 10 subsets, and the model will be trained and tested 10 times on different splits of the data. Let's recap. We are using random forest function, performing 10-fold cross-validation to evaluate the model during RFE. Next, we will perform RFE on the breast cancer dataset. RFE is the function that performs recursive feature elimination, and here is what each part does. Data. This specifies the matrix for feature, excluding the 10th column as it represents the dependent variable. This is the dependent variable, which indicates the class label, whether the cancer is benign or malignant. This specifies the different numbers of features to evaluate during RFE. In this case, RFE will evaluate feature subsets of size 1 to 5, meaning it will try using one feature, then 2, then 3, and so on up to 5 features. RFE control equals control. This passes the control parameter we set up earlier, which include using random forest for RFE and performing 10-fold cross-validation. To solve the previous error, we needed to install the package random forest. Now, let's run the code. Finally, this line will print the results of the RFE process. The output includes the best subset of features based on the model performance, ranking of features in terms of their importance for the model, the accuracy and other performance metrics for the different sizes of feature subsets. To sum up this step of our tutorial, we follow the 4 steps to perform RFE using R. We load the caret library to access the tools needed for feature selection. We set up the control parameter for RFE, specifying that we want to use random forest to evaluate feature importance, and apply 10-fold cross-validation to assess the model performance. We applied RFE on the breast cancer dataset. We evaluated feature subsets of size 1 to 5. We printed the results, showing the best features selected by RFE and their ranking, as well as the model performance metrics. This is a concise example of using RFE to reduce the number of features any dataset, while ensuring that we maintain good model performance. Before we close, I want to take a moment to acknowledge the strength and resilience of breast cancer patients and survivors. Your courage in facing such a challenging journey is truly inspiring. Whether you're currently battling breast cancer or are a survivor, know that you are not alone. There is an entire community standing with you. Keep pushing forward. Continue to trust in your strength and never lose hope. Together, we will keep raising awareness and supporting research for a future without breast cancer. You are warriors, and your fight gives others hope. Stay strong, stay empowered, and never stop believing in your healing and recovery. Best of luck. So that was it for today's video. A hands-on guide to dimensionality reduction using PCA and RFE with a high-dimensional dataset like breast cancer dataset. These techniques help simplifying your data, making machine learning more efficient while preserving the most important information. If you found this video helpful, don't forget to like, share, and subscribe for more data science content. If you have any question, feel free to leave a comment below. See you next time with more data science tutorials. Bye!